So we're going to take a break from polynomials for a minute, and we're going to review what you guys know about complex numbers today, and then we're going to go back to section 2.3 and we're going to finish our solving and factoring polynomials. So if you want to talk about complex numbers, it all starts with the number I. Now I stands for imaginary, and I is what we call the imaginary number, and we say it's the square root of -1. That's why it's imaginary. With real numbers, you can't take the square root of a negative. Imaginary numbers are us saying, like, what would happen if you could. Now, a complex number has two parts, has real and imaginary. So our standard form of a complex number is z equals a plus bi, where a is the real part and b is the imaginary part. And basically, here's a good way to think of it. Real numbers are anything that doesn't have an I in it. Anything with an I in it is an imaginary number. Those two groups combined are what we call complex numbers. Complex numbers is everything. All right, so when it comes to operations, meaning your basic math operations, add, subtract, multiply, and divide, the first three are really simple. Adding, subtracting, and multiplying with complex numbers. I said here, just treat I like a variable. Pretend it was x, and do the same things you would do. Do combining like terms, do foiling, do distributive property, whatever you need to do. Dividing is a little tricky, so I'm separating that. But let's do a quick example. Oh, and also, let's remember that I squared is -1. That basically comes from what I gave you on the last slide. If the square root of -1 is I, and you square both sides of that equation, it tells you that I squared is -1. So throughout these problems, if you ever end up with I with an exponent on it, you want to simplify that. All right, let's just put them all up here. So what we have is three examples: an addition problem, a subtraction problem, and a multiplication problem. Now the two in the left-hand column, adding and subtracting, very, very simple. It's just combining like terms. So like right here, as soon as I see that this is an addition problem, I don't even need the parentheses in this one. I'm just combining my like terms. So I say 3 plus 7 is 10. -2i plus 1i would be -1i. So I'll just put 10 minus I for my answer. It's that simple. And the same on the second one, you're just combining like terms again, you just got to watch out for the double negatives. So right here, when I'm subtracting, what I have is 4 minus 3, that would be 1. And then I have -7 minus -2i. That's actually going to turn into -7i plus 2i. So what we get here is minus 5i there. So subtracting really isn't any harder than adding. You just got to watch out for those double negatives and be careful. Now the third question over in the right-hand column, that's multiplication. And you really want to be careful here because you got to know what you're doing. You know, the fact that there's no symbol in between the two sets of parentheses, they're just stuck together, that's what tells you it's multiplication. And if, you know, on a quiz or a test, if I see mistakes on this type of problem, it's usually from people doing the wrong thing. Like if I give that first problem that I worked out in blue there and people start multiplying. Or if I give you this problem and people just combine like terms. But this is multiplication. And remember, you're doing it just like an X. So I'm going to do FOIL. I'm going to distribute. So I do 5 times 4, that would be 20. 5 times 3i, that would be plus 15i. I do -2 times 4, that would be -2i times 4, that would be -8i. And I do -2i times positive 3i, that would be -6i squared. Now, the one thing that you can obviously do is you can combine your like terms in the middle there. You have 20, that would be plus 7i minus 6i squared. Now, if this was x instead of I, if that was a variable, you'd be done. But remember what I said, I squared is -1. And when you're doing these multiplication problems, when you do I times I and you get I squared, you don't want to leave it. It's never simplified if you have exponents on your I. So what you want to do realize that that I squared is actually -1, which turns that into a +6. -6 times -1 is +6. And then you can combine it with the 20. So for your final answer here, you have 26 plus 7i. So that's multiplication. It was basic foiling, but you have remember that extra step at the end where you want to turn the I squared into -1 and simplify. All right, so the fourth operation is dividing. I said that's a little trickier, and before I can talk about dividing, I want to review with you guys the concept of conjugates. Now, a conjugate is when you have a binomial, two terms, and then you have another one that's exactly the same, but they have different signs in the middle. One has a plus and one has a minus. So for example, like the obvious one is if you have both terms, 3 plus 4i, 3 minus 4i. Those are conjugates. It's the exact same binomial, but one has a plus and one has a minus in the middle. Now the second example I gave you just to show you that, yeah, 2i and -2i are also conjugates, because what it really means is 0 plus 2i and 0 minus 2i. And that's not as obvious because you're used to seeing two terms, but those count as conjugates also. Now, here's the reason conjugates are important. Anytime you multiply complex conjugates, the answer is a real number. So basically the I part will disappear every time, and your answer will just be a regular real number like 10 or -17 or something like that. So let's do one of those. This is good because number one, it's one more practice multiplying problem, but also you'll see, I think, why conjugates work out. So this is 7 minus 2i times 7 plus 2i. They're definitely conjugates, same number, but one with a plus and one with a minus. If we start multiplying, you have 7 times 7 is 49. You have 7 times 2i is positive 14i. You have -2i times 7 is negative 14i. And then you have -2i times positive 2i would be -4i squared. Now what happens is, remember we said the i's cancel out? They do. -14i and positive 14i cancel out. Now the reason is, when you're foiling, if you're doing conjugates, you have the exact same numbers on both binomials, but one has a plus and one has a minus. So when you do outside times inside, you always get the exact same number, but one has a plus and one has a minus, like the 14's there, and they cancel out. Then what you do is the same thing we just did. You say that I squared is actually a -1, so this becomes 49 plus 4, and my answer is just 53, just a real number. That's what we were saying. So that's an important thing for you guys to remember. If you ever need to turn a complex number into a real number, you can do it by multiplying by its conjugate. And the reason that's important is we're going to use that for dividing. So this is number 4. Numbers 1, 2, and 3 we grouped together. Add, subtract, multiply. We said, okay, we can kind of do that pretty easily. To divide complex numbers, number 1, if it's not already like that, write it as a fraction. Remember, fractions mean divide. So if it's actually written out with the division symbol, 2 plus 4i divided by 5 minus 7i, put the first one over the second one. And the reason we do that is because with a fraction, one of the rules is you're allowed to multiply by anything you want as long as you multiply the top and bottom by the same thing. So we're going to multiply the top and bottom by the conjugate of the bottom, the denominator. Remember, not the top. We really don't care what happens on top. But if we turn the bottom into a real number, then we can separate the two fractions and we basically have our answer. So that might sound a little confusing. Let's do an example, and I think you guys will see how it works out. So we have a division problem here, 4 plus 3i divided by 9 minus I. And I said, before anything else, just write it as a fraction. So instead of divided by, I'm going to write it as 4 plus 3i over 9 minus I. Now then I said, the work for this, what we're going to do is we are going to multiply top and bottom, put all this in parentheses, by the conjugate of the bottom. Remember, we want the bottom to turn into a real number, not the top. So what I'm going to multiply is 9 plus I. Remember, you're not multiplying by the bottom itself. You're not multiplying by 9 minus I. You're multiplying by the conjugate of the bottom. And the reason is, what we want to do is turn that into a real number. So let's do, what we actually have is two separate multiplication problems. So on top, I have 4 times 9 is 36. I have 4 times I is plus 4I. 3I times 9 is plus 27I. And then I have 3I times I would be plus 3I squared. Now on the bottom, I have 9 times 9 is 81. I have 9 times I is plus 9I. I have negative I times 9 is negative 9I. And then negative I times positive I is negative I squared. And what happens, because we use conjugates on the bottom, those 9 i's cancel. They always will. That's what conjugates do. So if we clean this up a little bit, on top we have 36. If we combine our middle terms, we have plus 31I. And then that I squared will be negative 1, so that'll end up being minus 3 on top. And on bottom, we have 81, and then that minus I squared minus a negative 1 will end up being plus 1. So what we get, if we combine like terms on top, 36 minus 3 is 33 plus 31I all over 82. Now the last thing you want to do, remember at the beginning of the notes I said standard form for a complex number is a plus bi. You always want your answer to look exactly like that. Some real number plus some number times I. So the last step for this to get our final answer, just take each of the two numbers from the top. Let's see, I'm missing a 1 there, huh? 31I. Okay. Just split it up. You know, you put the 33 over 82 plus put the 31 over 82 and then put that I on the end. And that's standard form, A plus BI. So the real part is 33 over 82 and the imaginary part is 31 over 82. And you do get kind of ugly looking fractions like that, but that's how it works out. So the idea for dividing, you're actually doing multiplying. You write it as a fraction, you turn the bottom into a real number using conjugates, and then you separate and simplify. All right, the last thing I want to review with you guys today, because whenever you're talking about imaginary numbers, you're talking about the square root of -1, so there's going to be some radicals, some roots involved tonight. I want to review some properties with you. Number one, when you're adding or subtracting radicals, just think of them like a variable. You know, if you have two x terms, you can combine them. If you have two y terms, you can combine them. If you have an x and a y, leave them separate. Same thing with radicals. If I have two things with a square root of 2, I can combine them. If I have two things with a square root of 5, I can combine them. If I have a square root of 2 and a square root of 5, I leave them separate. So they work exactly like variables. So here's an example. If I have the square root of 3 plus the square root of 3, I can add them together and have two of them. It's like x plus x is 2x. Well, the square root of 3 plus the square root of 3 gives me 2 square root of 3. Or here's one with some coefficients. 5 root 7 plus 8 root 7, just add them up, 13 root 7. And here's an example of what I was saying does not work. If you have 2 plus the square root of 3, don't change it, just leave it. Don't try to give me square root of 5, that's not the right answer. It's just 2 plus the square root of 3, you just leave that. Okay, for multiplying, this one actually is a little easier. The rule is, yeah, you can do it. I mean, yes, it doesn't matter what the numbers are. You are allowed to do it. So yes, the square root of 3 times the square root of 2 does equal the square root of 6. I mean, very simple and straightforward for that one. Or for this one, if you have a coefficient, you can multiply separately. I took the 3 times 4 and got 12. And then in the square root, I took the 5 times 2 and got 10. So my final answer was 12 radical 10. Okay, now reducing or simplifying radicals. So the rule is, whenever you have a radical for an answer to a question or something, you always want to see if you can reduce it or simplify is another word for that. And what you're looking for is any perfect square factors. If that number can be divided by 4 or 9 or 16 or 25 or 36 or any perfect square, you always want to pull that out. You want to reduce that. So here's an example. We have the square root of 18, and I notice that 18 is 9 times 2, and 9 is a perfect square. So what I'm doing here, and normally I probably wouldn't even show this work, but I did it for the notes. I broke it up, and I basically used the multiplication property backwards. On the last slide, I said if I have square root of 9 times square root of 2, I can just multiply it and get square root of 18. Well, that works backwards too. If I have the square root of 18, I can break it up into the square root of 9 times the square root of 2. And the reason I did that is because the square root of 9 is 3. It's a perfect square. So my reduced or simplified answer for square root of 18 would be 3 radical 2. And that's because this one here is a perfect square. Now the one that's not a perfect square, you just leave. The square root of 2 just stays part of my answer. So the square root of 9 I simplified into a 3, the square root of 2 stayed there. And remember, you only do this with perfect squares. If I took this square root of 18 and I separated into the square root of 6 times the square root of 3, which you're allowed to do, I mean, that's right, 6 times 3 does equal 18, but neither of those simplified, so there's no point in doing that. So you only want to do that when one of the numbers is a perfect square and you can turn it into a whole number. And that's the concept behind simplifying. So the last thing is negative, and this is what's really new for this section. This is how you get complex or imaginary numbers. So if you ever have the square root of any negative number, so really like what we've been talking about is I as the square root of -1, but by having I as the square root of -1, it allows you to take the square root of any number. Because all you have to do, if you have the square root of -17, you can basically just turn it into the square root of +17 and then stick an I on the end. Or you can put it out front if you want. It's not inside the square root though, make sure you know that. The I comes out of the square root and then the number becomes positive. And really, you know, I should write this into the notes too, but what you're actually doing is the same thing we did when we simplified. You're saying the square root of -17 is like the square root of 17 times the square root of -1. Because +17 times -1 is -17. Well, this one right here is I. So what this actually ends up equaling is the square root of 17 times I. And that's exactly what we got. But like I said, we usually think of it as a shortcut, where if you have the square root of any negative number, just turn that number positive, stick an I on the end, and you got an imaginary number. So what I want to do, let's finish up with one example. We're going to evaluate, we want to give a simplified version of this answer. We have -18 times square root of +98. Now what I want to do is, I want to show us how we could do this one without using a calculator. You could go, because if you had a calculator and you multiplied, you would have the square root of, and then whatever 18 times 98 is. I don't have a calculator on me, so I don't know. But you're starting to get this big number in the thousands, and that becomes much harder to simplify, to reduce. So what I'm going to do is I'm going to simplify each one separately. I'm going to say, first of all, let's take this square root of -18. Let's get the negative out of there. Let's turn it into square root of 18 times I, and I'll leave the 98 for now. And then let's simplify each one of those. The 18 we've already done. The square root of 18, now 18 is 9 times 2. And the square root of 9 is 3. So I get 3 radical 2. I still have that I in the middle. And then we go over to the 98. Now if you start running through your perfect squares, it's not divisible by 4 or 9 or 16. It ends up being 49 times 2. And 49 is 7 squared. So I'm going to write this as the square root of 49 times the square root of 2, or basically 7 times the square root of 2. So if you start putting things together, what we have is 3 times 7 is 21. We still have that I in the middle. And then you have the square root of 2 times the square root of 2, which is the square root of 4. But that can also be simplified. The square root of 4 is 2. So what we have is 21 times I times 2, and 21 times 2 is 42. So my final answer is 42I. It took a little bit of work, but you guys can see I did it completely in my head or by hand on paper. I didn't need a calculator for that. If my first step had been to multiply 18 times 98, I can't do that simplifying without a calculator. I can't figure out that whatever number that is ends up being 42 squared. But you guys get the idea. That was a good way of working with radicals. And that's what you're going to see in the assignment today. You're going to have some working with radicals, but we're focusing on complex numbers.